In this video we talk about sequences. What do we mean by a sequence? A sequence can be thought of as a list of numbers written in a definite order. The elements of the sequence, this can be written as using the symbols A1, A2, A3, A sub n up to infinity. So A1 if it's infinite sequence. Now the first element here is called the first term. The second one is the second term. This is the third term. This is the nth term, etc. Now the notation that we use for sequences, we can list all elements or all terms of a sequence. We can write it by listing all elements, or we can write it in more compact form as a sub n, and n starts at 1, for example, to infinity. Or we can write it without using the index. Without determining the starting value of n and the ending value. We can write it this way. For example, this is a sequence n over n plus 1 from n equals 1 to infinity. Now if we want to find the numbers or the terms of this sequence, we need to substitute n equals 1 first, and then n equals 2 and n equals 3 up to infinity. So let's substitute n equals 1. When n equals 1, we get 1 over 1 plus 1. Now if we substitute 2, we get 2 over 2 plus 1. If we substitute 3, we get 3 over 3 plus 1, etc. And then we simplify more to get 1/2, 2/3, 3/4, 4/5, 5/6, etc. These are the terms of this sequence, and it's better to put them in a set notation. Now this expression represents the nth term of that sequence, and this is the first term, this is the second term, the third term, etc. But n does not have to start at 1. For example, look at this sequence, square root of n minus 3 from n equals 3 to infinity. As you can see here, it starts at n equals 3. So let's find some elements of this sequence. Square root we substitute n equals 3, we start at 3, so this is 3 minus 3, and then we substitute 4, we get 4 minus 3, substitute 5, etc. And that gives us 0, 1, square root 2, etc. Now how to find the nth term of a sequence? Finding the nth term of a sequence. To find, if I give you some numbers like these numbers or these terms, and I ask you to find a formula or the nth term, this term. For example, I may give you the sequence 3, 6, 9, 12, 15, etc. Now if I give you this sequence and I ask you to find the element, the nth term, you can find first, make a correspondence with the natural numbers. This corresponds to the 3 corresponds to the number 1 of n of natural numbers, 6 corresponds to 2, 9 corresponds to 3, 12 corresponds to 4, to 15 to 5, etc. So here we ask ourselves, what is the number whose multiplication by n gives these elements, or whose multiplication with by n and adding some number or subtracting number can give us this sequence, or what is the operation that can give us this sequence? So if we think, we need to think about this. We need to find some pattern. So if we multiply n by 2, if we multiply n by 2, the first element, 1 times 2 gives 2, 2 times 2 gives 4, 3 times 2 gives 6, and so on. So 2 is different from 3, 4 is different from 6. So the difference between 2 and 3 is 1. The difference between 4 and 6 is 2. Difference between 6 and 9 is 3. So it's not easy to find a pattern by if we multiply by 2. Let's multiply by 3. If we multiply by 3, we get, for example, multiply 1 by 3, you get 3. Multiply 2 by 3, you get 6. Multiply 3 by 3, you get 9. 4 by 3, you get 12. 5 by 3, you get 15, and so on. So that means the general term is a sub n equals 3n. Now if I give you another sequence, if I give you the sequence 2, 5, 8, 11, 14, etc., and I ask you to find the general term of this sequence. Now same thing, this corresponds to 1, this corresponds to 2, to 3, to 4, to 5, etc. Those are natural numbers. Now we need to multiply 1 by some number to get 2. So let's multiply by 2. If we multiply by 2, I mean to write 2n, multiply by 1 by 2, you get 2. Multiply 2 by 2, you get 4. Multiply 3 by 2, you get 6. Multiply 4 by 2, you get 8. Multiply 5 by 2, you get 10, and so on. So we didn't get the elements of that matrix, because that sequence, because as you can see, 2 is equal to 2. That's good. But the second element is 4 here. 4 is different from 5 by 1. And 6 is different from 8 by 2, and so on. So it's not easy to find the pattern by multiplying by 2. Let's multiply by 3. If we multiply by 3, we get 3 here. We get 6. We get 9. We get 12. We get 15, and so on. So if you look at this, we have 3 corresponds to 2. The difference is 1. 6 corresponds to 5. The difference is 1. So we get the number 8, but we get the corresponding numbers but reduced 1. We have to reduce 1 in order to get these numbers. For example, 3, in order to make it 2, we need to subtract 1. 6, to make it 5, we need to reduce 1. 9, to get 8, we need to reduce 1. So this is the pattern. This is the general term, and so on. So you need to think about the problem, try some numbers, and by doing more and more exercises, you get you'll have some experience in finding these patterns. Now let's continue here. There is a sequence, well-known sequence, that's called Fibonacci sequence, and this is a very important sequence. It has many applications in nature. So the value, this sequence consists of the following numbers: 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, etc. Now the question is there some relationship between these terms? Now we start this sequence with 1 and 1, and then we add, and from that point on you keep adding up the last two numbers. For example, 2 comes from adding 1 to 1. 3 comes from adding 1 to 2, the two previous numbers. 5 comes from adding 2 to 3. 8 comes from adding 3 to 5, and so on. This sequence was developed in the 13th century by Italian mathematician who solved a problem concerning the breeding of rabbits. Now, what is the general term of this sequence? The general term, as you can see, the first term is 1. So let's call this, instead of using A1, A2, let's use F1, F2. So F1 is 1 and F2 is 1 as well. Now what about the third term? The third term comes from adding the first to the second, and the fourth term can be obtained by adding the second to the third, and so on. So we can write a formula for this. If 3 here represents n, then we need to add n minus 2 plus fn minus 1, or fn minus 1 plus fn minus 2. For example, f5 is f4 plus f3. And here, so we can write the general term as f1 equals 1, f2 equals 1, and fn equals fn minus 1 plus fn minus 2 for n greater than or equal 3. So each number of the sequence is simply the sum of the previous two terms. Now we talk about a very important concept here, limit of a sequence. What is a limit of a sequence? If we are given the sequence n over n plus 1, where n starts from 1 and ends to infinity, we get 1/2, 2/3, 3/4, 4/5, 5/6, and so on. So if we look at the graph if we try to graph this sequence, this is the horizontal axis. The horizontal axis represents n, and the vertical axis represents a sub n. And here 1, 2, 3, 4, 5, 6. Here we have 1. Now the first element, this corresponds to 1, this corresponds to 2, 3, 4, 5. So when n is 1, we have 1/2. When n equals 2, we have 2/3. When n equals 3, we have 3/4. And when n equals 4, we have 4/5. when n equals 5, 5, 6, 6, 6 sevenths, and so on. As we can see, this sequence approaches some value, approaches 1. The height is 1. So this sequence approaches 1 as n goes to infinity. The sequence goes to 1, approaches 1, where n is sufficiently large and goes to infinity. So we can write limit of a sub n goes to infinity, which is equal to limit of n over n plus 1 as n goes to infinity, and we then, this is equal to 1. But how do we get 1? We can apply L'Hopital theorem, because substituting infinity gives us infinity over infinity, and this is one of the L'Hopital's forms. The L'Hopital's forms 0 over 0, infinity over infinity. So we can apply L'Hopital rule, L'Hopital's rule, by differentiating the numerator and denominator separately. What is derivative of the numerator? 1. What is derivative of the denominator? 1. 1 over 1 gives 1, and that's the limit of the sequence. So we may write n, the sequence n over n1 plus 1 from 1 to infinity approaches 1 as n goes to infinity. Now, in general, a sequence a sub n has a limit L, and we write limit a sub n goes to infinity equals L. This is true if we can make the terms a sub n as close to L as we like by taking n sufficiently large. In this case, we call the sequence a sub n convergent sequence. Otherwise, it's divergent. A sub n is divergent. Let's take an example. Is the sequence a sub n equals n over square root 10 plus n convergent or divergent? So in this case, we take the limit as n goes to infinity of n over square root 10 plus n. Now if we substitute infinity, we get infinity over infinity. We can apply L'Hopital's rule. So we find the derivative of the numerator and derivative of the denominator separately. What is derivative of the numerator? Is 1. What is derivative of the denominator? Derivative of the square root of 10 plus n is 1 over 2 square root 10 plus n. Now flip the denominator. We get 2 square root 10 plus n. Now substitute infinity, you get square root infinity, which is infinity. That means the sequence n over square root 10 plus n is divergent. Let's take another example. If we want to find the limit of the sequence ln n over n from 1 to infinity, so let's take the limit as n goes to infinity natural log of n over n. If we substitute infinity, we get infinity over infinity. So we apply L'Hopital rule. If we apply L'Hopital's rule, we get limit of what is derivative of natural log n? It's 1 over n. What is derivative of n in the denominator? It's 1. So that means we have limit 1 over n and goes to infinity. Now substitute infinity, 1 over infinity is 0. So this sequence is convergent because it gives us some constant L. So the sequence natural log n over n from 1 to infinity is convergent. Another example. If we are given a sequence -1 to the power n, n from 1 to infinity, we want to see if this is convergent or divergent. Let's graph this sequence first. So if we graph this sequence, this is n, this is a sub n, where this expression represents a sub n. Now we take 1, 2, 3, 4, those are some values of n. Now let's determine some terms of this sequence. We have -1 when n equals 1, 1 when n is 2, -1, 1, and so on. So it's alternating sequence. So when n equals 1, this gives us -1. Let's say this is -1 and this is +1. When n equals 1, we get -1. When n equals 2, we get 1. N equals 3, we get -1. And when n equals 4, +1, and so on. So as you can see, it's alternating and it does not converge to some specific value. So that means this limit does not, the limit or the sequence does not approach a number. So limit of -1 to the nth, n goes to infinity, does not exist. So the sequence -1 to the n, and from 1 to infinity is divergent. Now we have another concept. We can classify sequences into increasing, decreasing sequences. So we talk about sequence a sub n is increasing if a sub n, the nth term, is less than the n plus 1 term for all n greater than or equal to 1. And the sequence a sub n is decreasing if a sub n is greater than a sub n plus 1 for all n greater than or equal to 1. And the sequence a sub n is monotone if it is either increasing or decreasing. Now if we are given the sequence, for example, the sequence 3 over n plus 5, n from 1 to infinity. If we look at some terms of this sequence, we get when n equals 1, we get 3/6, n equals 2, 3/7, 3/8, 3/9, etc. Now, as you can see here, the numerator is constant and the denominator is increasing. So that means this sequence is decreasing. because here we have 1/2, this is 1/2, this is less than 1/2, and so on. So these are, for example, the term a sub n is greater than a sub n plus 1, and if this is correct, that means the sequence is decreasing. Now we can prove this by using this inequality. A sub n is greater than a sub n plus 1. So substitute n, we get 3 over n plus 5. Want this to be greater than, substituting n plus 1 in this sequence. So this gives us 3 over n plus 5 greater than 3 over n plus 6. Added those two numbers, and then we can see that the denominator here is greater than this denominator, and as we know that the larger denominator means the smaller value, and that means this is correct. So a sub n is greater than a sub n plus 1. So the sequence for all n, let me write it in words, for all n greater than or equal to 1, or in natural numbers. So the sequence 3 over n plus 5 is decreasing. Now let's take another example. If we have the sequence n over n squared plus 1, and we want to see if this is to show that this sequence is decreasing. So in this case we apply, if it's decreasing, then a sub n is greater than a sub n plus 1. Now we substitute n, so that gives us the same general term, n over n squared plus 1, greater than. Now we need to substitute n plus 1 for the term a sub n plus 1. We get n plus 1 over n plus 1 squared plus 1. Now we simplify the right hand side. N squared plus 2n plus 1 plus 1. This one. Simplify more. N plus 1 over n squared plus 2n plus 2. Now we cross multiply these. So we get n times n squared plus 2n plus 2 is greater than n plus 1 times n squared plus 1. Now to make sure that our answer is correct, we can substitute some values and see if the inequality is satisfied. So let's try n equals 1. If we substitute n equals 1 here, we have 1, 1 plus 2 plus 2. This is 4, 5. 5 in the left hand side, and here if we substitute 1, we get 2 times 2, that's 4. So 5 is greater than 4. Now let's continue. So this is n cubed plus 2n squared plus 2n greater than n cubed plus n squared plus 1. And then we can cancel this with this. So we have n squared here. Let's subtract n squared. We get n squared plus 2n is greater than n plus 1. Let's subtract n. We get n squared plus n greater than 1. Is this correct? Let's substitute 1. N equals 1. We get 1 squared plus 1 is greater than 1. Let's substitute 10. 10 squared plus 10 is greater than 1. That's correct. So that means the sequence is decreasing. So the sequence n over n squared plus 1 is decreasing. Now we have some other concepts like the sequence is bounded if there exists some constant m, this is constant, such that a sub n is less than or equal to m for all n greater than or equal to 1. So in this case we call the sequence bounded above. This is bounded above. And the sequence a sub n is bounded below if there is little m such that little m is less than or equal to a sub n for all n greater than or equal to 1. Now if the sequence is bounded above and below, then the sequence is called bounded. If the sequence a sub n is bounded above and below, we call it a bounded sequence. Now let's take an example. If we have the sequence n, where n from 1 to infinity, this sequence is bounded below because if you write some elements, some terms, 1, 2, 3, 4, etc., the smallest value is 1. So this is bounded below. This is bounded below, but it's not bounded above. But not bounded above. So not every bounded, let me leave this as a blank, so we want to write the correct answer here. Not every bounded is divergent or convergent. So if we take the following example, if we have a sequence -1 to n, where n from 1 to infinity, we find that the elements are -1, 1, -1, 1, -1, 1, etc. So this is an alternating sequence, and the a sub n, this is a sub n, is between -1 and 1. So it's bounded. This is bounded sequence. But is there a limit? Or if there is a limit, that means it's convergent. Is there a limit for this? The answer is no, because if we graph this limit, we find that this does not converge to some specific value. So this is bounded but not convergent. So not every bounded is convergent. We can find bounded sequence that is not convergent. And the bound M, let's back to this description here. The bound M, the upper bound M, if we graph the function, the sequence, and let's say the terms look like this, and this is L, so this is the limit of the sequence. The upper bound can be a value here. This is M. This is an upper bound. Now back to limits and some theorems on limits. If the limit of the absolute value of a sub n goes to infinity is equal to 0, then as a result the limit of the original sequence is equal to 0. For example, if we want to evaluate limit of -1 raised to power n over n approaches infinity, in this case it's not easy to find it directly by substituting infinity. So the theorem says that if you find the limit for the absolute value of a sub n, so let's take the absolute value of a sub n. So absolute value of a sub n is absolute value of -1 to n over n, but we know that -1 to power n gives us -1, 1, -1, 1, -1, 1, etc. Under the absolute value, this is always equal to 1, because if it gives us -1, absolute value of -1 is 1, and the denominator stay the same, n, sorry. So limit of 1 over n goes to infinity. This is limit of absolute value of -1 to the power n over n approaches infinity. Substitute infinity, 1 over infinity is 0. So if the limit of the absolute value of the sequence is 0, then the limit of the sequence, without using the absolute value notation, the limit of the original sequence, -1 to the nth over n goes to infinity, is equal to 0. Now why is this is correct? Because if we want to graph this sequence, the sequence -1 to the nth over n, here this is nth axis, this is a sub n, and this is 1, this is -1, here we have 1, 2, 3, 4, 5. At negative, if we substitute n equals 1, we get -1. Substitute 2, you get 1/2. Substitute 3, you get -1/3. Substitute 4, you get 1/4. Substitute 5, you get -1/5, and so on. So as you can see, the sequence is convergent, and it converges to 0. As you can see, the height becomes closer and closer to the nth axis, the horizontal axis, and that means the height becomes 0 eventually. So this sequence, -1 over 1, 1/2, -1/3, 1/4, -1/5, 1/6, etc. This is -1 over to the power n over n. This converges to 0 as n approaches infinity. Another theorem, another useful theorem, says that if the limit of some sequence, some convergent sequence, is L, and the function f is continuous at L, at this limit, then as a result, limit of f of a sub n as n approaches infinity is equal to f of L of the limit or limit value. What does that mean? Let's take an example to explain this. So if we have limit of sine pi over n goes to infinity. Now we have a sequence and we have a function. This is the sequence a sub n, and this is the function f. So we have a sequence inside the function f. So if that's correct, that means we can insert the limit inside this function. So this gives us this gives us sine, use different color, sine of limit of pi over n. We just take the limit of the sequence, and that is sine of, what is limit pi over n? Pi over infinity is 0. Sine of 0 is 0 because the sine function is continuous on its domain. From the sine is a continuous function. Okay, so the last thing, just a note: not every monotone sequence is convergent. Not every monotone. We mean by monotone sequence the increasing sequence or decreasing sequence. Not every monotone sequence is convergent. If the sequence is bounded and monotone, then it is convergent.